Hi, everyone. Thanks so much for coming this morning. We actually have a couple of us presenting today. I'm Oliver. This is Wenwen, Shang, and Michael. And we're going to be talking to you about a project called Firebird that we did last summer as part of the Atlanta Data Science for Social Good program. And this was in collaboration with the Atlanta Fire Rescue Department. So the problem here, like many cities, there are hundreds of fires that occur every year in Atlanta. And one way to reduce fire is to actually inspect the buildings that are at risk of having fires so you can eliminate potential fire hazards. But only a small percentage of the properties in Atlanta were actually being inspected each year. And one of the reasons that this was happening is because it's really hard to figure out which properties actually should be inspected out of all of the properties in the city. And there are a lot of different ways that this can be accomplished with data, but the problem is that the data comes in all different formats from all different sources and different departments and organizations. So it's often very difficult when these departments aren't talking to each other and when the data is so different. So we had two different questions that we wanted to address. The first was, how do we help the Atlanta Fire Rescue Department identify new properties that need inspection? So they were only inspecting a small portion of the properties that actually needed to be inspected. And the second question is, once we have this list of properties that should be inspected, how do we help them prioritize by fire risk so that they can inspect the properties that are most at risk of fire? So we're going to be talking today about the Firebird Framework. And this is a picture of what we're going to be talking about. So at the top, we have all of the different data sources that we put together in order to understand the answers to these questions that we're trying to address. And once we had the list of properties for inspection, we then developed a predictive model that would tell us which of these properties were most at risk of fire. And then with all of that information, we made an interactive map that we could then give back to the Atlanta Fire Rescue Department so that they could inspect those properties that they needed to inspect. So I'm going to talk just a little bit about the data sources that we had. So this is a list of all of the different data sources, and they are a couple different categories. So the ones in bold here are data that are about fires, and this is coming from the Atlanta Fire Department. We also have data about businesses coming from a few different sources, such as the City of Atlanta and something called the CoStar Property Report. We also have data about business licenses, and then we have data about particular geographic areas and the demographics of those areas. And I'm going to hand it over to Wenwen, who's going to talk about how we joined all of these different data sources together.
Okay, so in order to identify the potential inspections, we first started looking at the current inspections that the fire department is doing, and then cross-reference it with the business license data we obtained from the city of Atlanta, so that we can get a first look at what type of businesses are currently being inspected. And then we find similar kinds of properties from the rest of the business license data set, and also some business we found in the Google Places API. And eventually we remove the ones that seems duplicated in the data sets and come to a unique list. And this chart shows you the top 6 currently inspected properties by the city of Atlanta. And the blue bars representing the ones they are currently inspecting, while the orange bar shows you the similar potential inspections that could have been done with similar property types. So as you can see, there are a lot of potential inspections for them to do. So in addition to the 2,500 properties that they are currently inspecting, we identified 6,000 more properties using the top 100 currently inspected property types. So the eventual list we provided them also included the property names, address, phone number, and business types. In addition to that, we also maintain the ID number, unique ID numbers from different business data sets, so that in the future, if they need more information, they don't have to go through the text matching process we went through just to identify them directly using those unique numbers. And also, as I have talked, that there are many potential inspections, but the human resources in the fire department is quite limited. So we also attach the fire risk scores to each property so they can prioritize the entire inspection process, which will be our objective too. So far we are mostly done with the objective 1, and now we move on to do a machine learning model to help them to prioritize the entire inspection. So we started with the commercial property that list that is purchased by the Atlanta Fire Department, which contains information like number of floors, year built, owner information, and material of the structure, etc. These information are quite sufficient if you want to lease the offices for potential other commercial uses. However, it's not quite sufficient to build a predictive model. In addition to that, we also need further information on the properties, such as whether the property has caught on fire, and what business is inside the property, and whether the property has been inspected before, and what's the typical condition of the property. So fortunately, we obtained all those data sources from different departments all over the city of Atlanta. So the key questions becomes how to actually connect those data sets together, because they don't have unique IDs to join them. So what we did is to actually join them based on geographical information like coordinates, addresses, and parcel ID, so that they can form a comprehensive look of all the properties in the city of Atlanta. So here is just a short view of the eventual outcome of all the joined data sets, so we can have like different conditions and employment density, building environment information about each typical property, commercial properties in the city of Atlanta. And then by the end of the day, we have 252 different variables we can play with in the machine learning models that Shang is going to talk more about.
Okay, so to prioritize fire inspections, we built predictive models to generate a fire risk score for each commercial property. In our data, we have about 8,000 commercial properties with about 500 fires from 2011 to 2015. And we use the data from 2011 to 2014 to predict the fires in 2015. Because we have heterogeneous data that comes from different sources, so we need to do a sequence of preprocessing steps. The first step was to do feature selection. We used forwards and backwards feature selection and selected 58 most predictive variables. And next, it's common for a merged data set to have a lot of missing values. So we filled in those missing values with zeros. But to distinguish between true zeros and missing values, we add another binary feature to indicate whether it's missing or not. For categorical features, variables, we expanded it into binary features using one-hot encoding. And for numerical values, we normalized it into 0 to 1. But for large numerical variables like sale price, we first used log transformation. And for machine learning models, we tried several popular algorithms like logistic regression, SVM, gradient boosting tree, and random forest. And among them, we found that SVM and random forest perform best. So here are our experiment results. As you can see, SVM can predict 71% of fires at a 20% false positive rate. So considering that we only 6% of the properties in our data had fires, so our result is much more predictive than random guessing, right? And random forest has a slightly lower true positive rate of 69%, but it has at a same false positive rate, but it achieves a higher overall AUC. Now, we don't want to be just lucky in predicting fires in a particular year, so we tried training on several time windows and predict the fires in the next year, in the following year. And we found that the accuracy is quite consistent in predicting different years. The 2011 to 2012 training window is slightly worse due to lack of positive examples because the training period is shorter. But still, it's significantly better than guessing by chance. So finally, it is helpful for us to, and for the Atlanta Fire Rescue Department to know which features are the most predictive, effective predictors. So we list the top 10 features in the random forest model, ranked by the ratio of examples split by it. So collectively, they capture the intuition that the buildings of larger size or those containing more units, so more people, would have higher probability of catching fire. And now Mike will talk about how to use these predictive models to guide the fire inspections.
So as Shang mentioned, we wanted to be able to actually use this fire risk score to help the Atlanta fire inspectors improve and prioritize their inspection process. So we used the results from the SVM model, the most accurate performing model that we had, to obtain the raw prediction output of their likelihood of having a fire. Here, the red are the true positives, or the buildings that actually did catch on fire in our model, and the black are the true negatives. And so we then assigned, the negatives. So we then assigned those to a risk score from 1 to 10 and a risk rating low, medium, and high. We then applied that in our data set, which we provided to the fire department of the actual properties. So their names, of course, and addresses are blurred out here for privacy reasons. The property type, which Wenwen spoke about, she mentioned an example of the, say, restaurants in the city. The fire department knew about roughly half, through no negligence on their fault, but through the messiness of the data. So we were able to provide them, in this example here, of restaurants that they might not already have known about with their associated risk rating, numerical score, and then the category low, medium, and high. So this we provided to them in the form of this database. But we also wanted to give them a interactive tool that the fire inspectors could use in their daily inspection planning operations. So we plotted the fire incidents and their currently inspected properties onto an interactive map using D3 and Mapbox, and also then plotted these potential inspections onto a map. So I'm going to do a quick demo here for you. So this is the city of Atlanta. This is a quite zoomed out view. You can see here in red are the fire incidents, or the places around the city that had fires previously in the last 5 years, and they can filter by the date, or they could filter by the property type, so looking only at the residential or non-residential fires. They could then also, in green here, look at the currently inspected, or the places that they already knew about, that they have been inspecting, as Oliver mentioned, for the last 5 years, these 2,500 properties. And they can, their process is every year, on a cyclical annual basis, they inspect properties exactly a year to the month from when they're previously inspected, which is stipulated by the fire code. So they can look here and say, okay, we want to inspect the restaurants. We know there have maybe been fires recently in some restaurants. So we're going to look and see what of the restaurants in the city, which do we not already inspect. So for instance, for a fire inspector going on their daily inspection process, if they're going here to this particular restaurant, they might be able then to be more efficient and pick up a couple of these new inspections. Now, this is all 1,200 of the restaurants, so you might want to say, okay, well, what about only those medium and high risk restaurants? So now they can then target a little bit more specifically. We then wanted to also provide for the executive staff of the fire department, not just an individual property level, but an aggregate level. So the fire department uses a battalion system where they have different structures. Each fire station is in a battalion. and the council districts so they can look at an aggregate level. So if you'd like to see that more in depth, please come by our poster tonight, and we'd be happy to do a live demo for you there. So as you saw, some more detail, and you can see an overlay level with percentages for each of those. So we provided to the fire department this database, as we mentioned, of these 6,000 new properties, a predictive model using a false positive rate of 20%, because in our model we wanted to account for when the false positives were the properties that were very similar to the structures that had fires. So our intuition was that they would also want to inspect those places. We were more tolerant of false positives, and we provided them with the interactive map. So recently, in the last few months since we transferred this to them, of course, 6,000 new properties, they can't triple their inspections overnight without drastically increasing their personnel, but they did target the high-risk properties. Of the 69 high-risk properties, they found 48 fire safety violations, 27 that had out-of-date permits, 13 that required new permits, and only 14 that did not require permits. So our impact on their planning process, helping them inform their personnel allocation, maybe different neighborhoods, different battalions of the city, rather than the even distribution of fire inspectors across each of the battalions. Maybe the places that had more fires or more risky properties should be assigned more inspectors. And then also, as Oliver mentioned, one of the difficulties, and Wenwen talking about the data joining process, this has started to drive conversations between the fire department, the Department of Buildings in the city, to help them share these building registry, building identification codes across departments, which will help the technical process immensely. And also helping inform the fire code policies, which require annual inspections for all properties that meet the criteria, but yet perhaps not all the properties require an annual inspection. Maybe some require more frequent or less frequent. So this work has been highlighted as a best practice from the National Fire Protection Association for using data to inform and improve fire safety practices, and we've been working with them to help them generalize this model for other cities. Some of our future work is improving the models using more dynamic behavioral data about property usage, perhaps noise violations, pollution, trash violations, those sorts of behavioral data that might prove informative, and then extending them to be more applicable to more properties in the city and generalizing for different municipal areas. So we encourage other fire safety organizations or municipal governments to use our framework to help identify and prioritize their property inspections. Thank you.
Thank you. It was very interesting. I have two questions about, first, the historical data, the likelihood of a commercial place to be in fire. How is it related to the historical data of this specific location on being fire? Was this something, one of the features that you discussed? Second question is, what about the effectiveness of the inspection? Did you build a model to analyze this impact?
So to your second question about the effectiveness of the inspection, interestingly, what surprised us, the properties that received inspections were actually significantly more likely to have fires in them, which seems counterintuitive, except that the properties that require inspection are those with flammable materials and things like that. And so we are working with them to help integrate that dynamic data about those inspections in the model, but it's not something that we have in there right now. And then your first part about the historical data?
Yes.
So you're referring to historical beyond. So we used 5 years worth of fire data in building the model. Or were you referring to historical as prior to that, or which part?
When the prior place was in fire, was it more likely or less likely to be in fire?
Yes, yeah, right. So that was definitely a significant predictor of future fires. Yeah.
Hi, I have a question about how you treat missing values. So you said you have impute it with zeros and then add an indicator with 1 or 0, like a binary indicator. Why don't you use the mean or the majority vote? Because zeros can be informative. Sometimes we're not centered around 0. So I was just wondering why are you
So because the variables are very sparse, so a lot of the variables, only a few of them have values. So for those variables, we fill in missing values with zeros, but actually there are a few of variables that have only a few missing values. So for those variables, we actually fill in with the mean. Right.
Oh, okay. And for like categorical variables, you're like, how do you deal with that?
So we make it into binary indicators. So if there are like n categories, we expand it into n binary indicators. Right?
Okay, thank you very much.
Hi. Could you pull up the slide where you showed the features which were top features?
Yeah.
It's further down, further back.
That one. Yeah.
Yeah. So these were for the risk or for the potential places where fire could happen, or is it for the risk score?
For the risk of fire.
For the risk. So all these to me seem very generic. So why there's nothing very specific, like floor size? So does it have, what kind of correlation does it have with prediction? Is it larger floor size, higher risk, or lower risk? Same for the land, number of units, appraisal value. But all these still are very generic to me. Why is there no predictor like how many customers do they get? If it's what kind of a establishment it is. Is it a restaurant? Is it a club? You know, if you put that as one of the predictors, and why did they not come up as predictors? Because all these are very generic to any business or any residential property. So any comments on that?
So first, this is just the first 10 useful variables. So some of the variables you mentioned may be in the also very useful, but we're not showing here. And some of them, like more dynamic or behavioral variables, we don't have them now.
Oh, but did you have others, like how many number of customers are they getting every day?
No.
So we are limited by the data sources. So the primary one that was most informative were these community investment reports and a real estate property evaluation that looked at the structural features. But definitely some of these, right, so floor size, land area, number of units are positively predictive of fire, and I believe total taxes was negatively predictive of fire. There's more detail in the paper. We'd be happy to talk a little bit more about for each of the specific ones, which
Okay,
direction
so
it goes
last question.
tonight. Yeah.
So since you had the information about the previous fire, so there must be a reason for, let's say, origin of fire. So let's say the origin of fire was something happened in the kitchen. So did you have any predictors from that? Because it must be common in all the restaurants and clubhouses. If they say that the fire happened because somewhere near where chef was working, so you know how many units of gas do they have? Did you put any of that in the predictor model? Since you would have all that information from previous, you know.
So we did have information from the fire department about the cause of the fire. So there are some kitchen fire, trash fire, things like that. But so I think for us, so many of them were kitchen and trash, it ended up not being informative. And we ended up just using the binary, was there a fire or not, as the predictor. But as far as the location of the gas outlets and things, we didn't have that granularity of information, unfortunately.
Great, thank you very much.
Okay, so we have many people who want to ask questions. So each one only ask one question, okay?
My question is basically this. Did you consider the unbalanced nature of your data and the impact it might have on a couple hundred predictors, 500 fires?
Yeah, so we did talk about other models, maybe like lasso or maybe some ridge regression or something like that. We weren't able to for this work, but future work potentially could use more, right, to be able to account for the fact that our P is similar to our number of positives. Is that what you're referring to?
Yeah. The other strategy is just use synthetic data to try to augment your data set.
Bootstrapping, yeah. Cool, thank you. Yeah, we'd be happy to talk further.
Hi. Can you tell me a little bit about the politics of the situation? Because, for instance, it would be obviously nice to use the reports from the fire inspectors. Presumably, violations are predictive. Is there any possibility of getting that? I mean, how cooperative is the fire department with you guys and things like that?
Sure. So we actually did spend quite a bit of time with the fire inspectors. We actually went out into the field with them and observed them filling out paperwork. And the problem with this is that it all really is just paperwork still at this point. It's not computerized. The parts of it that are computerized are very difficult to interpret. It's a lot of qualitative, like just typing in things that would be really hard for us to interpret. And so it was quite difficult because there are a very limited number of fire inspectors, and we're kind of almost did hear some fear about increasing their workload to a great extent. And so I think that's why the prioritization is so important, because we were able to say, well, ideally you would inspect all of these properties, but we know that you can't. And so here is where you can really focus your efforts. And I think that helped a lot with that. Does that answer the question?
Kind of, yeah. I mean, yeah. I wonder if you could ask them, anyway. Yeah, ask for them for next year for a rating score of 1 to 5 on how likely the place is to burn down, and or something like that.
So we actually did. We actually did a focus group with the fire inspectors initially. So we went on ride-alongs, as Oliver mentioned, and then a focus group to elicit what they initially, before building the model, what they thought were some of the major predictive features. And it actually ended up being very similar to what we found here too. But there was the resistance about increasing the workload.
Last question.
Yeah.
Right?
You compared your false positive to random selection, which is very impressive, the ratio. But these firefighters, they are professional. Probably they have some intuition. Did you try to compare this to what they would do without yours, which is probably better than random selection?
Yeah, that's a good question, and we didn't specifically do that. But thank you. It's a good suggestion.
Definitely for the identification of new properties, their existing process for finding a new property was ad hoc, amounted to visually discovering a new property while driving around the city. Thank you.
Okay, due to the time limit, so we need to start the next talk. Okay.